So in the last class, we have done interval estimation. Okay. Now we are doing the maximum likelihood, that is the section 7.4. So in the last class, you suggest me that I always mention the section number of your book. So here it is a section number 7.4. That is the maximum likelihood estimation. And this is the estimation as considered as a point estimation. So earlier also I told you that there are 4 types of estimation. But basically we are doing point estimation, interval estimation, hypothesis testing, and significance testing. Okay, so point estimation we have done for unbiasedness. Now we are doing the another one, that is known as the maximum likelihood estimation. Interval estimation we have completed in the last class, correct? Any query in that one? Thank you. So now this is the maximum likelihood estimator. So what we are doing, as the name suggests, we are doing the estimation. That is also we can consider as a point estimation, because we have done the unbiased estimation. If you remember, in the point estimation means what? We are saying X bar is an unbiased estimator for mu. Okay. Mu is what? We are consider mu as population mean, and X bar is what? Sample mean. So we are estimating the mu by using the X bar, correct? That we have done. And we have just defined that expected value of that X bar is equal to mu basically. So this is the relationship between these two. Okay. So that is the relationship between the X bar and mu here, that it is their unbiased estimator of this. So we are using the term unbiased estimator. So in the initial level, we have done the unbiased estimator for the population parameter. Now we are also done that expected value of S square is equal to sigma square. So we can say that S square, that is the sample variance, is an unbiased estimator for population variance here. Okay, so that is also an unbiased estimator. Now we are just doing the maximum likelihood estimator. So it is a most widely used parameter estimation as on today. The basic principle is to maximize the likelihood of the parameter. So firstly, we have to find out what is the likelihood function, and then we are maximizing it by using the calculus, which you have done earlier. Okay. So firstly, what is the likelihood function? Likelihood function is the function of the model parameter theta. So here we are doing for mu, so that theta is equal to mu basically. Okay. So whatever the parameter is, accordingly, we can identify what is theta, and then we can find out its likelihood function. Okay. So theta can be a single parameter or a value vector of parameter. So it may be 2 parameter or 3 parameter. Okay, just like a normal distribution, we have 2 parameters, mu and sigma. In gamma distribution, we have the 2 parameters, alpha and beta. But in exponential distribution, only 1 parameter, it is beta. है ना? So in the geometric distribution only 1 parameter, that is p. Poisson distribution only 1 parameter, that is lambda or mu. Okay. So based on a lambda only, we can calculate the mu. So that is the concept which we are using here. To just theta 1 and theta 2 may be more than 1 basically. The likelihood function is defined as the product of the probability density function, okay, with the different values of xi. So that is the what is we are taking here. We are taking the joint probability density function. Do you remember in the chapter we have done joint distribution? So we are using here the joint density function, and this is a random sample basically. So you know the random sample, the meaning of the random sample, that the all values x1, x2, xn are identical and independent. Okay, so if they are independent, the joint density function is equal to the product of the marginal density function. Now they are just identical, so that's why they have the same density function. Okay, but here xi is different, so that is become here product of marginal density function to make it joint density function, and this joint density function is considered as likelihood function. Okay, now we are just maximize it. Okay, and it will become very difficult to maximize maximize it, the product. Okay, so that's why we are taking the logarithm. And why we are taking the logarithm? That it is a one-to-one function, and maximization of log will, which is give the likelihood function, is often preferred to computational case. Okay, so to just make the computational easy, we are using the logarithm of the likelihood function, and they will give the same point because it is a one-to-one mapping. So when logarithm of likelihood function is maximum, same the likelihood function is maximum, and we have to find out the maximum point. Correct? So we are using that same here, likelihood function. Okay, so that is the method is known as maximum likelihood function. So firstly we have identified the likelihood function, and we are maximizing it. And in the maximization process, it is difficult. So to make it easy, what we are taking, we are doing the logarithm function. Okay, so once I obtain a random sample from a distribution of a random variable x with density f. Okay, because it is a random sample, so they have the same distribution, identical distribution. So it means density function is f for all, and associated parameter is theta basically. Correct? So now we are defining the likelihood function, that is the product fx1, fx2, fx3 up to fxn. So that is what the joint density function, which is the product of the marginal density function, because they are independent. Okay, and they are identically distributed. So that's why we are using only f. That's because they have the same density function. Okay, now it is a known as likelihood function for the sample. Now we are taking the logarithm for. So find the expression for theta that maximize the likelihood function, and this can be done directly, but it is difficult to do that directly. So we are using the logarithm of theta, of ln of theta, of L theta, and then we are maximizing it. Okay. Now, after at the last moment, we can just replace the theta by the theta hat. Why we are taking the theta hat? Because theta hat is the estimator. Do you remember that we are saying the sigma square estimator? Hai na? This hat sign we are using to make the estimator. So we are replacing the theta by the theta hat to define the expression for the estimator. Okay, now some sample values are provided. So we just plug in the values in the formula, obtained formula, and we can find out the our maximum likelihood estimate. Correct? Any query in the theory part? Please reply me back. Okay, thank you. Okay, now we are doing a one example so that you can understand this theory very well. Okay, first is we are taking a normal distribution. So you know the density function of the normal distribution. You know that there are two parameters of the normal distribution, mu. No, exam in exam theory will not come. Definitely it is not. It will not come. It is some numericals are coming. The questions only, because it is an open book examination. So theory we can't give the theory. Okay, so let x1, x2, and this is the just a step. Okay, just a step to do, or this is just an algorithm to find out the or to do the questions basically. Okay, that's why the theory is not coming in the examination basically. Okay, let x1, x2, xn be a random sample from a normal distribution with the mean mu and variance sigma square. Correct? So you know it very well that normal distribution, the parameters are mu and sigma. So if you know the mu and sigma square, then you can define its density function as this. So fx is equal to 1 minus square root of 2 pi sigma e to the power minus half x minus mu upon sigma whole square. Okay. You know this density function of the normal distribution. In chapter 4, you have already done it. Now, likelihood function for a sample is a function of mu and sigma. So there are two parameters we are taking. That is theta 1 is equal to mu and theta 2 is equal to sigma here. So in particular, this is the log our likelihood function. This one, it is 1 upon. So do you remember, do you forget about the density function of normal distribution? That is fx is equal to 1 upon square root of 2 pi sigma e to the power minus 1 by 2, 1, x minus mu upon sigma whole square when x is greater than 0. No, x is also between minus half. Oh, I'm sorry. I don't know. Okay. So we are just taking the product of this. I is equal to 1 to n, and in this one, this has become xi here. Different. Acha. Actually, that is the difference because here we are taking the square root of under root 2 pi. Okay, because we are just taking here sigma square here, so it will become in the square root here. Correct. But if we are taking 1 upon 2 pi and then sigma, this is completely. Because you can see we are just taking yes. Okay, sigma is outside from the square root, so that's why become it is sigma only. So we are just taking, we are multiplying it for the n times. So we can say this is the constant term. It is multiplied by n, so power n. Now e to the power minus half sigma square. So it is square is taking outside from this. And because it is in exponentials, we are multiplying it exponential function. So it will become, oh sorry, it will become summation of xi minus mu whole square. Okay, when we just multiplying it. So now it is very difficult to take the maximization point of this because here the power is there. Okay, and we are just differentiated. What we are doing into the find the maximization, we are taking the differentiation. Okay, with respect to the parameter and putting this is equal to 0. The differentiation part is equal to 0. That we are doing here. Okay. So same here, it is very difficult to take the differentiation with respect to mu and with respect to sigma. So what we are taking the logarithm of it. So we are saying logarithm of L become minus n, okay? Or you can write like this one. Fx that, okay, I will just do it here. Logarithm function will become here 1 upon square root of 2 pi sigma whole to the power n e to the power minus half sigma square x minus summation I is equal to 1 to n xi minus mu whole square. Correct? So now we are just taking the logarithm. So ln of L will become n times of logarithm of 1 upon square root of 2 pi into sigma minus, because we are taking logarithm of this function, so it will become logarithm of e is equal to same, so 1 upon 2 sigma square summation I is equal to 1 to n xi minus mu whole square. Correct? And in this part will become here, because it is 1 upon this, so we are taking here minus sign and we are just remove this 1 upon. So that's why what we have done, minus n ln of under root 2 pi minus n ln of sigma and minus 1 upon 2 sigma square summation of I is equal to 1 to n xi minus mu whole square. Now you got it. So it is a simplification when we are taking the logarithm. Now it is easy to take the differentiation and put it is equal to 0 to make it maximum function. Correct? So we are just doing it to maximize this function. We take the partial derivative. Why we are taking the partial derivative? Anyone can tell me? I'm waiting for your reply. Why we are saying it is a partial derivative? Because here we have the two parameters, mu and sigma. Correct, Mr. Sanjeev. Okay, multiple variables, mu and sigma. So we have to differentiate with respect to mu and is equal to 0. We have to differentiate with respect to sigma and put it is equal to 0. But there are two parameters. That's why we are taking the partial differentiation. When there is only one variable, we are taking only simple differentiation. Correct? To minimize the function, nahi, to maximize the function. Yes. Okay. So that's why we are taking the partial derivative with respect to mu and sigma and set these derivative equal to 0 to make the maximum. Okay. So solve the equation simultaneously for mu and sigma. So you will get the two equations because you are just taking del of ln of L upon del mu is equal to 0. And you are also taking del of ln of L upon del sigma is equal to 0. So two equations and two unknowns, that mu and sigma, and then you can find out the value of mu and sigma, which is equal to the mu hat and the sigma hat. Yes, which formula you are talking about, Mr. Vineet? It is a density function for the normal distribution. So it is given in the question that it is for a random sample we are taking from the normal distribution. Correct? So if we are taking from the normal distribution, then we are just taking a normal density function. We taking the product of this normal distribution density function n times. So we are getting the likelihood function. Okay, we simplify the likelihood function. It is coming this. Now we are taking the logarithm of the likelihood function because logarithm is making a easy calculation. So that's why we are taking here this after simplification we are getting this one. So it is a very simple formulation. Basically, when we are using the logarithm, we are applying the properties of the logarithm. Okay. Now we just take the differentiation here. So we are taking del upon del ln of L, del ln of L upon del mu is equal to 0. So our equations was what? If we're just saying here, ln of L is equal to, I will just write it here so that it is become easy. Minus n ln of under root 2 pi minus n ln of sigma minus 1 upon 2 sigma square summation I is equal to 1 to n xi minus mu whole square. Okay. Now we are just taking the differentiation with respect to mu. So del ln of L upon del mu, okay, is equal to 0, which will provide in the left hand side. This is a constant with respect to mu. So that's why the depend we are taking differentiation, it is coming 0 minus this is also constant with respect to mu because here no mu. So that's why this is also 0 minus 1 upon 2 sigma square. Correct. So that's we are saying here 0 minus 0. Now 1 upon 2 sigma square is coming here with minus sign. Now we have to differentiate it with respect to mu. Okay. So we differentiated with respect to mu. So what is coming here? That is coming minus 2 times of summation I is equal to 1 to n xi minus mu. Okay. So that will become equal to 0. And when we are just saying 0 is 0, minus sign, this minus sign is become plus. 2 is 2 cancel out. So it will become 1 upon sigma square summation I is equal to 1 to n xi minus mu is equal to 0. Now I got it. Okay. Now we can just take the sigma square because sigma square never be equal to 0. Why? Because it is a variance. So variance never be equal to 0. If variance is equal to 0, then xi is not a random variable. Okay. So from that, we are just finding summation I is equal to 1 to n xi minus mu is equal to 0. Now we can say we just open this summation. So summation I is equal to 1 to n xi minus n mu, because we are just adding mu n times mu. Okay, so that will become n mu and just put it is equal to 0. So it is equal to the summation n mu is equal to, so summation of I is equal to 1 to infinity is equal to n mu. And from that we can say mu is equal to summation I is equal to 1 to n xi upon n. And then when we are using the equal sign, then it is become mu hat. And this is the estimator. And this is what? Which formula is this? That is x bar. Okay. So we are just taking here this. Then mu hat is equal to x bar. Is it clear to all of you? So x bar is also, we already identified, follows an unbiased estimator. It is an unbiased estimator. So that is an unbiased estimator. But by using the maximum likelihood estimator, we also find out in the normal distribution that is the same. No difference at all. Okay. Now, del of what? Del sigma ln of L is equal to 0. Correct? So now, our ln of L is what? Minus n ln of under root 2 pi minus n ln of sigma minus 1 upon 2 sigma square summation I is equal to 1 to n xi minus mu whole square. Correct? Now we are just differentiated with respect to sigma. So del of ln L upon del sigma, which is we are putting equal to 0. So first term is no sigma, so that will become 0 minus n. What is the differentiation of ln of sigma? when we differentiated with respect to sigma. Do you remember? Anyone who is remembering, they can recall. No, ln of x, d of ln of x, dx is equal to what? 1 upon sigma, correct. Not 1, 1 by sigma, correct. Okay, so it will become here n by sigma minus. Now it is 1 by 2 sigma square. Okay, so it will become again plus, because we are taking sigma minus 2 here. Okay, so it is become, or I will write it like this, minus of 1 upon 2, and it will become minus 2 into sigma per minus 1, and this is the same, I is equal to 1 to n xi minus mu. Okay, and then we are putting it is equal to 0. So those two terms are coming here, and this is 0 here, 0 we can remove here. Okay, so it will become here minus n by sigma. This 2 is to cancel out, minus minus t plus 1, and it is n cube summation I is equal to 1 to n xi minus mu, and that is equal to 0. Okay, now we simplify it. We can just take the n cube common here, and it will become minus n sigma square plus summation I is equal to 1 to n xi minus mu, just to avoid the denominator, and we can just take this sigma cube is multiplied by the 0. Why? Because it is not equal to 0. Okay, so the finally we are getting minus n sigma square plus summation I is equal to 1 to n, and that we can use also, open the summation, I is equal to 1 to n xi minus n mu is equal to 0 here. Okay, so here we are just saying sigma square by this, or we are not opening it. Without opening also we can do it, that it is summation I is equal to 1 to n xi minus mu whole square is equal to 0. Okay, so sigma square is what? We are just taking this side and divided by n. So it is summation I is equal to 1 to n xi minus mu. Yes, correct. I'm sorry, I just missed this square term. Thank you, Mr. Randhir. I missed that point. Okay. So sigma square and mu is unknown. So instead of mu, what we are using? We are using x bar, because we have already identified that mu bar is equal to x bar. This is the final formula for MLE of sigma square. Earlier we are using in the denominator n minus 1 to make it unbiased estimator. Here we are using n. So they are different. So this is not an unbiased estimator. Mu hat is equal to x bar is an unbiased estimator, but here sigma square hat in this MLE, that it is not an unbiased estimator. Okay. Now come to the next question. X1, X2, Xm be a random sample of size m from a binomial distribution with parameter n and p. N is known to us and p is unknown here. Okay, find the maximum likelihood estimated for P here. So only one parameter is P. So we are just taking the total differentiation here. Okay. So what is the density function of the binomial distribution? If x follows the binomial distribution with parameter n and p, do you remember fx? That is what? ncx p to the power x 1 minus p to the power n minus x when x is equal to 0, 1, 2 up to n. Otherwise it is 0. So this is the density function. Now we are multiplying it. Okay, and p is also between 0 and 1. So we are just taking here likelihood function L, that is the product of I is equal to 1 to n. NCX can be written as NCX can be written as NCX. है ना? So we are using the same thing, NCXI p to the power xi 1 minus p to the power n minus xi. Correct? There is, here we have to write the NCX, but there is no need to remember, find out the NXI. Okay, so this we have done in the slides also. Now we are taking the logarithm of it. Firstly simplify and then taking the logarithm. So we simplify it. So first condition is coming here. Product of I is equal to 1 to n NCXI. Okay, this is the first product. Now p to the power summation of xi, because xi is in the power. Okay, similarly we can say 1 minus p to the power summation n minus xi. Okay, I is equal to 1 to m. I is equal to 1 to m here. Correct. Now that will become 1 minus p to the power nm minus summation of xi. Now we are taking the logarithm of it. So logarithm of it is the log of this part as it is. Now this one is this is in the power. So summation of xi ln of p, summation nm minus summation of xi ln of 1 minus p. Okay, we have to take the logarithm. Now here only one parameter, that is p. So that's why we are taking the differentiation and we are saying d of ln of L upon dp is equal to 0. Okay, so in this case you can see there is no p. So then we differentiate it, this is equal to 0. Okay, this will become here 0. Plus here p is there, but it is ln of p, तो differentiate करेंगे, so summation of I is equal to 1 to m xi upon p. Okay, similarly in the next term plus nm minus summation of xi is equal to the 1 minus p ln. Okay, and because it is minus p, so that's why this will become here minus and put it is equal to 0. Okay, the term is coming here. Okay, put it is equal to 0. So nm minus summation of xi, we can just take like this one. Summation of xi, I is equal to 1 to m upon p is equal to nm minus summation of xi, I is equal to 1 to m upon 1 minus p. So 1 minus p is going this side, p is going this side. So summation of I is equal to 1 to n xi into 1 minus p is equal to nm minus summation 1 upon I xi multiplied by p. This is the same expression. Okay. Now we can simplify it and put it is equal to 0. After, so what we have done, we have taken 1 minus p upon p, nm minus summation of xi divided by summation of xi. In this one, we simplify it, 1 minus p minus 1. And this one will become again summation minus xi. So it will become p hat is equal to summation of xi upon mn. M is the sample size and n is the variable binomial distribution. So that's why x bar summation of xi upon m will become as x bar. So we are saying here x bar upon n. the binomial estimator for the you can say the maximum likelihood estimator for binarily distributed random variable x with parameter p. Okay, so that is the estimator of p. Just give me a 1 minute. I want to drink the water. Just give me a 1 minute. Welcome back. So up to here, any query? Am I audible? Thank you. So any query? Now we are doing for exponential distribution. So in the X be an exponential distribution with unknown parameter lambda. So we have to find out the maximum likelihood estimator for lambda based on a sample of size n here. So what is the density function for exponential distribution? The density function is lambda e to the power minus lambda x, correct? So we are taking the product of this. So it is become lambda e to the power minus lambda xi. So it will become here what? When we are taking L is equal to lambda to the power n e to the power minus lambda. And here it is the power. So it is xi, correct? Now we are taking the logarithm of L. So it will become n ln of L lambda minus lambda summation of I is equal to 1 to n xi is equal to 0. Okay, sorry. Okay, now d of ln of L upon d lambda is equal to 0. Okay, all steps are same. This is the simple algorithm. So it will become here n upon lambda minus summation I is equal to 1 to n xi and put it is equal to 0. So that will give you here n upon lambda is equal to summation I is equal to 1 to n xi, and that also provide you that lambda hat is equal to upon n is equal to 1 upon summation of xi, I is equal to 1 to n, and that will become here lambda hat is equal to n upon summation of xi, I is equal to 1 to n. So it is 1 upon x bar. Correct? Any query? Formula derivation means what? Density function? No, it is not asked. This is because this is the first step that you have to know the what distribution. So what is the PDF of that? Then only you can come. It is an open book examination. Okay, it's an open book examination. So you can just take the this PDF formula from the book. No problem at all. Okay, only you have to differentiate it, taking the logarithm and differentiate it, put it is equal to 0 and you will get the answer. Okay, so lambda hat is equal to 1 upon x bar. Some more example. What, Mr. Randhir? This type of question, I'm just doing the one question, Mr. Randhir. 3 questions we are doing. I'm saying the same type of question that can be asked in the examination, that type of questions, not that questions, that type of questions. Summation xi by n in the Poisson distribution, and we are talking about here exponential distribution. Okay, you are talking about, just check it. You are talking about the Poisson distribution. So lambda is a parameter in the Poisson distribution as well as in the exponential distribution. So we have done the question for the exponential distribution, not the Poisson distribution. So you are seeing the book for the Poisson distribution, not the exponential distribution. So be careful about it. Okay. I am taken the different questions from the examples which is given in your textbook so that you can do some more examples which is already provided in the textbook actually. Hai na? Now one more question, that it follows the Rayleigh distribution. Now you don't know the Rayleigh distribution. It is not given in your syllabus. Okay, so what we are saying, we are providing you the density function. Okay, even though it is an open book examination and we are seeing Rayleigh distribution, so you can identify, find out the Rayleigh distribution density function from the test book, no problem. But in that case, because we have not discussed anything about the Rayleigh distribution, that's why we are providing you the density function with parameters, correct? Now here theta is the parameter, okay? So any density function we can give here. NP, why lambda can be written as NP? NP is in the binomial distribution. Here we are talking about the Poisson distribution. Here we are talking about the lambda is coming in the exponential distribution. So we can't write it NP. That is a different concept which we have done earlier. That lambda is equal to consider as NP when we are approximate the probabilities by using the Poisson distribution. Question of the binomial distribution, and we approximate probabilities by Poisson distribution for large sample. N is large and P is small. Okay, so don't confuse as we have done earlier. That was the different contest. Here this is a different contest. Correct. That is the algorithm I told you. Take the density function of that distribution. Then we are taking the likelihood function, that is the product, and of the density function. All things are same, only x1, x2, xn we are changing. And then we are taking the logarithm of that likelihood function, and then we differentiate it with respect to parameter, put it is equal to 0, to maximize the log of likelihood function. That is the algorithm only. Correct, Mr. Randhir? So same thing here, density function is provided to you, nothing is required here. So what you will do? You are just doing here the logarithm function. Logarithm function is what? Pi is equal to 1 to n xi by theta e to the power minus xi square upon 2 theta. Okay, that will become likelihood function. Now we are taking the logarithm of, firstly we just simplify it. L will become here x1 x2 multiplied by xn upon theta to the power n. है ना, ये multiplication in the numerator. Then this is exponential, so it will become here e to the power minus 1 upon 2 theta, and summation I is equal to 1 to n xi square. Correct. Now we are taking the logarithm log of L. So it will become here ln of x1 multiplied by x2 up to xn minus n ln of theta minus 1 upon 2 theta, summation I is equal to 1 to n xi square. Okay. Now we are taking the differentiation with respect to theta. So d of ln of L upon d theta is equal to 0. Differentiate it. The first term, no theta, so it will become 0. Here n ln of theta differentiated, it is by theta minus 1 upon 2 summation of I is equal to 1 to n xi square. ठीक है ना? And then 1 upon theta differentiated what? Minus 1 upon theta square. Okay. Put it is equal to 0. This minus and this minus will become positive. So it will become here n by theta minus n by theta plus 1 upon 2 theta square summation of I is equal to 1 to n xi square is equal to 0. Now we simplify it. You can see here. Okay. So it will become like this one. We reached here, and to estimator, we just to simplify it, and we will get the theta is equal to summation xi square divided by 2n. Okay? Any query in this one to find out the maximum likelihood estimator? Now, I am just showing you the previous question. In the previous question, what is given here? Find out the unbiased estimator. Okay? So it, oh, sorry. Expected value of x square is equal to 2 theta, which is provided actually. Use this fact to construct an unbiased estimator for theta. So that is coming from the previous section, that is unbiased estimator. Okay. So what we are doing to find out the unbiased estimator, expected value of x square is equal to 2 theta implies that expected value of x square by 2 is equal to theta. Correct. So x square by 2 expected of this follows the theta hat is what? Summation of xi whole square upon 2n will be an unbiased estimator for theta. Okay, that is coming from here. We again check summation of xi square upon 2n. So we can take the summation common, 2n common, a summation of expected value of xi square. Expected value of xi square is what? Expected value of xi square, it is 2 theta. It is given in the question. Upon 2n, and 2n upon theta upon 2n is equal to 3 theta. So expected value of theta hat is become equal to theta. So that's why it is an unbiased estimator. Okay. Now estimate the value. N is equal to 10. Observations are provided here. These are the 10 values are given. So what you will do, because it is given here, theta hat is equal to summation of xi square upon 2n, and I is equal to 1 to n. So we are finding summation of xi square, that is what? 14390.1058. So theta hat will become here xi square, summation xi square upon 2n, we can say n is equal to 10, so it will become 20, and this answer is what? 74.505. Okay, so here I am just also recalling the concept of the unbiased estimator, how to do this question. And this is question for the maximum likelihood estimator. And you can see here, sorry. Okay. So unbiased estimator and the MLE estimator both are same. Summation of xi square upon 2n. Okay. Similarly, we can just do the uniform distribution. Okay, that part is not in your syllabus. Just cross it. Okay. So now we will do the test of hypothesis. So we have done the two type of unbiased point estimation. One is the unbiased estimator, which we have done in chapter 6 basically. Now we are doing the maximum likelihood estimator, which is the section 7.4. Correct. Now we are doing section 7.5, test of hypothesis. So before doing this, I will just take the break. Okay, to just go through this definition, and then I will come back to do the test hypothesis, that is section number 7.5. Correct. Am I audible? There was some internet issues which I'm trying to resolve. Am I audible? Thank you. Are the slides visible? No. Okay, I'm just wait. Now, okay, fine. Okay. There was some internet issue. Actually, I'm just trying to resolve it. So any query till now? So now we are just going for hypothesis testing. That is section number 7.5 here. Okay. According to your textbook. So as I told you, we are doing the point estimation we have done, interval estimation we have done. Now we are doing the testing of hypothesis. Okay. So we are just taking, this is a statistical hypothesis or just a hypothesis, is a claim or assertion either about the value of single parameter, okay, about the values of several parameters, or about the form of entire probability distribution. So we are just claiming something and we are giving the proper evidence by using the sample distribution that our claim is okay. We can just accept that claim or not accept to claim. Okay. So in any hypothesis testing problem, there are two contradictory hypotheses basically under consideration. One hypothesis might be the mu is equal to 0.7. So we are just taking a parameter, okay, the population mean and population variance we are talking about. In your syllabus, there is only mean, okay, population mean. We are talking always about the mu here, okay. So mu is equal to 0.75 and the other is considered as mu is not equal to 0.75. So these are the two contradictory hypotheses. Similarly, we can take P is greater than equal to 0.10 and P is less than 0.10. Okay. So the objective is to decide based on the sample information. As I told you, we have to give the some evidence based on the sample. So sample information is given and we have to identify which hypothesis is correct. So there are two hypotheses and we have to just find out based on the sample information that which is correct here. Now just take up a simple example. In a trial, jury must decide between the two hypotheses. The first is the null hypothesis. Okay. That is the prior belief. And that is the second one. So there are two hypotheses. One is known as the null hypothesis. Null hypothesis, it is denoted by the H naught, and second is known as the research hypothesis or alternate hypothesis. This is denoted by the HA. Okay, so the null hypothesis is means what? That is the prior belief. But what is the new claim? That is based on the HA base. Okay, so the prior belief that defendant is innocent, but the new claim is what? Defendant is guilty. Okay. So now we are just doing, we are presenting some evidence that we are just doing that for the new claim. Okay. But we have to check that, okay, that it is this hypothesis is correct or this hypothesis is correct. Okay. So the jury don't know which hypothesis is true. They must make a decision on the basis of evidence presented. Correct. The jury is saying here that there is enough evidence to conclude the defendant is guilty. Okay. or the jury acquits that it is stating that there is not enough evidence to support the alternate hypothesis. Not support, there's not enough evidence to support alternative hypothesis means what? We are going for the H naught. H naught is true. H naught is true means what? The defendant is innocent. Correct? So jury is not saying that the defendant is innocent, that they are saying there is not enough evidence to support the defendant is guilty. Okay. So they are not saying here directly all the things. They are saying in the form of we fail to reject H naught. Null hypothesis means H naught. So we are not saying we accept the null hypothesis. We are saying fail to reject H naught. Okay. So we are just fail to reject H naught or we reject H naught because we are giving the enough evidence. We are trying to present the enough evidence to support our claim. And claim is what? The defendant is guilty. But they are not finding, they find the proper evidence. So they were saying we reject H naught that the defendant is not guilty. Correct? But if there is not enough evidence in that in favor of the claim, so they are saying we fail to reject H naught. So there are two type of negation. Fail to reject H naught. It means what we are saying? H naught is accepted. So they are not saying he is guilty. Okay, or he is innocent. They are saying here we fail to reject H naught means what? We accept H naught means the defendant is not guilty. Correct? So that's the hypothesis testing we are doing here. One example I gave you in a real life example. Okay, so we have the two hypotheses. First is a null hypothesis denoted by H naught. It is a preconceived notation regarding the parameter value. The hypothesis to be contested. Okay, it is claim that initially assumed to be true. That is the prior belief claim. Correct? Next is the alternate hypothesis that is denoted by HA. The claimed or the proposed value. Okay, the new claim. So the hypothesis which we wish to establish actually. Okay, whatever the prior belief is coming, that is okay. Now based on the some other information, we are claiming a new one that is coming in a HA. It is assertion that contradictory to the H naught. So it always be contradictory to the H naught. Correct? HA is also referred to as researcher hypothesis because it is a claim that the researcher would really like to validate. Okay. Null hypothesis means no value, no effect, or no consequence. So that's why it is H naught should be identified with the hypothesis of no change. Hypothesis of no change, no difference, no improvement, and so on. So the equality sign always come in the H naught. That's why it is known as a null hypothesis. And the second is known as the researcher hypothesis, the alternate hypothesis. Correct? So in hypothesis testing, H naught will generally be stated as an equality claim. Always the equal sign will come into the null hypothesis. So alternate to the null hypothesis of H naught, theta is equal to theta naught. Theta to naught means specified number, which is the null value. Okay. And we will go for the three assumptions that HA maybe theta is greater than theta naught, theta is less than theta naught, and theta is not equal to theta naught. Okay. So these are the three assertions of the hypothesis testing, and equality sign always come into the null hypothesis. Okay. So theta is equal to theta naught, in which we implicit null hypothesis is theta is less than equal to theta naught here. Okay. And this is considered as right-tailed because theta is greater than theta naught. So that's why because of this the right tail. Theta is less than theta naught, left tailed, and theta is not equal to theta naught. It may be less than, may be greater than. So we are saying it is a two-tailed. Okay, as we have done in the interval estimation. Do you remember interval estimation? We are finding the complete interval. But later on, what we are doing, we are not taking the lower bound. We are just find the upper bound only, not the lower bound. Or we are just saying only a lower bound we are emphasize. Okay. So at the time, this is the one tail. And when we are taking the both and limits, then it become two tailed here. Okay. And how we can just give the enough evidence to validate our new claim, that is HA, we are using the test statistics. So it is known as the test procedure. Okay. So this section is 7.6 here. So 7.5, it is the hypothesis testing. What is the hypothesis testing that we will do? 7.6, we are defining as alternate and null hypothesis. What is it and how to define it? Correct. Then we are doing the test procedure. Test procedure is what? There are test statistics. Statistic we have done as the function of a random sample, and we are doing it for the testing. So that's why it is known as the test statistic. Correct. So it is a function of sample data on which the decision is to be based. What type of decision? That we reject H0 and we do not reject H0. Correct. And then we are just taking the decision based on the rejection reason. Okay. We are finding the complete reason. We are dividing the complete reason into the two parts, acceptance reason and the rejection reason. So if you remember in the interval estimation, we have done the same thing. So don't think that we are doing new thing here. If you remember, so this was the graph. Do you remember? Standard normal graph. And we are saying this is 1 minus alpha. And this is the acceptance reason. And this is the rejection reason. Okay. So there are two limits we are finding. This one. So it is in the acceptance reason. And here it is the rejection reason. Two tail we are talking about. Okay. So we divide the complete reason into the two parts. One is the rejection reason. And one is the acceptance reason. In the one tail. Okay. So this is the two tail. This is the one tail here. So how we can identify this is the rejection reason? It may be here. Okay. So that's we are finding set of all statistics value for H0 will be rejected. And that we can find out by the use of label of significance. Correct. That we will discuss. So null hypothesis will then be rejected if and only if the observed or computed test statistic values fall in the rejection reason. So we are calculated the test statistic, and if they fall in this particular reason, the rejection reason, then we can say it is H0 is rejected. That is the conclusion. Otherwise, if it is in this region, specifically AR region, so we are saying here that it is failed to reject H0 here. Okay. So when we are doing this one, because we don't know the exact value of theta naught. So what we are doing here, we are doing some error here. So there are two type of error, which is when we are rejecting H0 when H0 is true, and we fail to reject H0 when H0 is false. So the probability type 1 error is we rejecting null hypothesis when it is actually true. That is the probability of type 1 error. It is denoted by alpha. And type 2 error means what? Fail to reject H0 when it is false. Okay. So this is a probability of type 1 error, and it is denoted by beta here. And then 1 plus power of test. So 1 minus beta is known as the power of test. Okay. So the power of test is what? Probability of rejecting null hypothesis when it is false. So at the time, we are not committing any mistake. We are not committing any error. So it means that is the power of the test. Okay. Now, alpha value, that is the alpha, that is a type 1 error, probability of type 1 error. This is also known as the significance level here. So a type 1 error is an error made the null hypothesis is rejected in spite it is true. So the probability of type 1 error, committing a type 1 error, is called the level of significance, and it is denoted by alpha. So our emphasis, the rejection reason is coming from the alpha when we are rejecting H0. Okay. So that is coming alpha basically. So probability of type 1 error, probability of H naught. When H naught is rejected, given that H naught is true. So it is a conditional probability basically. The set of values of test statistics leads us to reject if the null hypothesis term is critical reason. So that's why this is known as the rejection reason or critical reason. So if test statistic falls in the critical reason, then we can say it is a H naught is rejected. Otherwise, we fail to reject H naught. Got it? Any student having any doubt in this one? So the brief is there are two hypotheses H naught and HA. Prior belief is coming in the H naught and H naught is known as the null hypothesis. Then equality sign always come into the H naught. Okay, which is the new claim by the researcher that is coming in the HA. Okay, so it may be three parts of the HA. Theta is greater than theta naught, theta is less than theta naught, and theta is not equal to theta naught. So both firstly 2-1 is the they are the known as one tail and the last one is known as the two tail because it may be theta greater than theta naught and theta is less than theta naught. So we are finding the error something. Okay, so this error is probability of type 1 error. Type 1 error is what? The probability when we are rejecting H naught when it is true. So we are doing mistake here. So that error we can find out. Okay, so we are finding the probability of type 1 error. Okay. Similarly, we can find out the probability of type 2 error. So that is known as the beta here. And we are finding the probability null hypothesis is not rejected when in fact the research theory is true. So we are saying it is a committing of type 2 error and it is denoted by beta here. Okay. That is the conditional probability here. And 1 minus beta is considered as the power of the test. Now constructing the null and alternative hypothesis. So we are firstly find out HA. Okay, what is the new claim basically? Just contradictory to that, it is H naught. Okay, equality sign always come into the H naught. So if theta is less than theta naught, we are taking the left tailed. Left tailed means what? The rejection reason, the critical reason in the left side of the graph. Okay, theta is greater than theta naught. It means right tail. That is the critical reason in the right side of the graph. Two-tailed, theta is not equal to theta naught. So critical reason is divided into the two parts, left tail and the right tail. Okay. So these are the three cases of the hypothesis testing. And these two are the alternate contradictory hypothesis, H naught and HA. Got it? Any query? Now we are just taking up one example here to construct the hypothesis. From long experience of Coca-Cola company, it is known that the yield is normally distributed. Okay, so population is given normal distributed with mean of 500 units and standard deviation is 96 units. Okay, so what information is provided? Population is normal. This is required to make a test statistic basically. Okay, and mu naught is given at 500 units and sigma is given as 96 units. Correct. For the modified process, now the process is modified and the X bar is coming 435 for the sample of size 50. Okay, so N is they are taking as 50 and X bar is coming here 435. This is by the sample. So they are done some modification in the previous some work, and then they are just saying 5% L significance level. Does the modified process decrease the yield? Decreased the yield. Okay, so this is the new claim that they are decreasing, and here alpha is equal to 0.05, 5%. Correct. So this information is given. Now we have to make the hypothesis. So what is the HA? We are talking about the mu, so mu. And then it is mu naught. And it is decreased. So we are saying decreased. Okay. So H naught is the contradictory of it. Mu is greater than equal to mu naught. And mu is less than mu naught means it is left tailed. Got it? Any query in this one? Please reply me back. Am I audible? No one is replying, so I don't know that am I audible or not. Okay, thank you. Okay. So we are saying here mu is greater than equal to 500 and mu is less than 500, left tail. Why? Because mu naught is equal to 500. Okay. Next. So here you can see here, this is the graph, and in the graph that is the left tail here. Now come to the next question. A department store manager determines a new billing system will be cost effective only if the mean monthly account is more than 170. So it is more. Okay, the new claim is what? More than 170. So here we can say here mu naught is given as 170 and HA is what? HA is what? Mu is greater than 170, mu naught. Okay. A random sample of 400, so n is equal to 400. They are provided. Monthly account is drawn, which is the sample mean is 178. So X bar is coming 178. It is known that accounts are approximately normally distribution, so population is normal. It is given information just to give the enough evidence. Mr. Dhamotran, right now we are not able to find out the answer, final answer, because for that test statistics is required. That we will do later on. Here I am just to define how how I'm just explaining how to define the hypothesis. Correct? The same question we will do later on when we are doing the complete statement. Okay? And with the standard deviation of 65. So sigma is also given 65. At 1%, so alpha is equal to 0.01. So HA is this. So H naught is what? Just opposite of this. That mu is less than equal to 170. Correct. Now mu is greater than 170 means what? We are talking about the right tail. So up to here we are discussing this concept only. So we are defining here this. Okay. So here it is mu is greater than 170 right tail and mu is less than equal to 170 as H naught. So here it is a right tail here. That is the rejection reason. Okay. Now we have to identify where the rejection reason will start. That is based on alpha. Okay. Next question. Same question we will do when we complete it. Okay. A drug is given to 10 patients and the increment is their blood pressure were recorded like this. It is reasonable to believe that the drug has no effect on the change on the mean blood pressure. So here, no change. So HA will be what? Mu is not equal to 0. No change in no effect. So mu is equal to 0. So it is what? Two-tailed. Okay. Now it is given n is equal to 10 and the alpha is equal to 0.05 significance level, assuming that the population is normal. and the variance is equal to 1. So n is equal to 10. Data points are provided here. So we can calculate the x bar as well. It is two-tailed. It is greater than, so right-tailed. It is not equal to two-tailed. Got it? That we will do, Mr. Mahesh. Actually, 5% level of significance we didn't use till now. है ना? Based on this 5% significance level, we are finding the rejection reason. That we will do later on. Just wait. So now one question. To test the null. Two-tailed. How we are just using the two-tailed? It is given in the slide, beta. This one. Mu is not equal to 0. It means it is two-tailed. है ना? So read the question carefully. What is the new claim? Accordingly, we can say here that what is the our HA? That is most important part of the hypothesis testing. Now we are doing a one question. To test the null hypothesis, the population mean is mu is less than, this is given mu is less than equal to 4. Against the alternative hypothesis that mu is greater than 4. Mu is greater than 4 means what? It is a right-tailed problem. Correct? So the rejection reason is coming in the right side of the graph. Correct? It is designed based on a random sample of size 49. So n is equal to 49, which rejects null hypothesis if it is observed sample mean is x bar is equal to 4.3. So x bar is 4.3 here. It is more than 4. Okay. Find the probabilities of type 1 error and type 2 error. So alpha. Alpha is the probability. Type 1 error. Correct? That is the probability when we reject H0, given that H0 is true. Okay. So when we are rejecting H0, when X bar, this sample is lie in the critical region. Okay. So it is right-tailed, rejection region in the right-hand side. So that is we are rejecting H0 when X bar is greater than 4.3. Given that H0 is true, V small, mu naught is equal to 4. Okay. Now you can just use it X bar. X bar we have already done by the moment genetic function. Do you remember that if population is normal, so X bar also follows the normal distribution. है ना? So it is follows the normal distribution. So we can convert X bar minus mu naught. What is the distribution of X bar is normal with the parameter mu naught and sigma upon root n. It is greater than, है ना? So 4.3 minus mu naught is 4. Sigma is given as 9. So sigma variance is given 9. So sigma is 3 upon a square root of n is 7. Okay. Now you can just calculate this value. So X bar follows the normal distribution with parameter mu and sigma upon root n. Sigma is given as 3. So we are just saying mu is equal to 4. We have to consider. Okay. So we are just finding this one, and that is coming probability when Z is greater than 0.7 and it is 1 minus. This is a standard normal distributed table. By using the table, we can find out this value is what? 0.2743. So alpha is equal to probability of type 1 error is what? 0.2743. So what is the significance level here we are talking about? 27%, which is very high. Okay. Similarly, beta is what? Probability of type 2 error. Type 2 error is what? Accepting null hypothesis when it is false. Okay, it is false, so we have to calculate it. So here we are taking mu is equal to 5, which is greater than 4. Okay, size is 49. So we just find out the probability of type 2 error is, again I am doing here. So probability, just opposite of that which we have done. So earlier we have done x bar is greater than 4.3. Here we are doing less than 4.3. Given mu is equal to 5. Okay, when h naught is false. So probability when x bar minus mu upon sigma upon root n is less than equal to 4.3 minus mu is equal to 5 upon 3 by 7. This is the same thing. And that is become here minus 1.63. And when we are finding the table in the standard normal distribution, CDF 0.0516. Okay, so when we done the normal distribution, do you remember I told you that it is very important in the statistics. So same thing we are doing. So normally distributed random variable is x bar. Now we are converting into the standard normal distributed parameter, and then we are finding the value by using the standard normal table. Got it? The CDF of the normal standard normal table. So in the hypothesis testing, first step we have done, set up the appropriate null hypothesis and alternate hypothesis. Okay. Second is, what is the critical point? So it is based on the alpha. Third, we define the critical reason, left side, right side, and what is the critical reason based on the alpha basically. Okay. Then next we are doing the calculation. So collect the sample data and compute the test statistic. So this is our test statistic basically. This is our test statistic basically. Okay, because it is a large sample size. So by central limit theorem, do you remember central limit theorem? X bar approximately follows the normal distribution. Okay, and then based on that calculation, we reject H naught if the calculated test statistics fall in the rejection reason. Otherwise, we fail to reject H naught. Okay. So that is the hypothesis testing 7.6. So now 7.7, when we are talking about the hypothesis of one mean. One mean what? We are talking about the same as mu. So some part we have already done. Mu is less than equal to 4. Mu is greater than 4. We are always talking about the mu here. Okay. All the examples I gave you for the mu only. So same thing we will do it here. So time is almost over. So I am just stop here. So I will upload the slide for this also, hypothesis testing concerning one mean. We are using these steps. These are the algorithms. Okay. So in the next class, we will continue from that hypothesis testing for one mean. Section 7.7. Correct? Any doubt? Any query? Quiz 2 is already opened. So please complete it in the